All right, third degree polynomials. These are called cubics because they contain x cubed. And the simplest cubic ever is y equals x to the third power. But then you can throw in terms with x squared and x and constants in them, and you can also put a multiplier out in front of your x cubed, and you can get their behavior to change that way. All cubics look kind of like s's or like lightning bolts. They'll have shapes like this or like this, that sort of thing. And they can go in the opposite direction too. So, some things they all have in common. Like all polynomials, they have domains that cover the entire real line. Cubics all have the same range, and it's always the real numbers. Oops, sorry, that's y. Can be any real number. Because they have tails going in opposite directions, they always have one end that goes up forever and one end that goes down forever, and so they cover every y value there is. And cubics always have just one y-intercept. Now, the graph of a polynomial function, the tame ones rise like this and have no turning points. They flatten out for a minute like they're going to turn around, and then they go, nah, I won't, and they just keep going in their original direction. The fancier ones rise, double back, and then double back again, and so they have two turning points. So this here looked like it was going to be a turning point and ended up not being. And this other version has two turning points. Changes direction and then changes direction back. And for x-intercepts, well, a cubic can't avoid hitting the x-axis. It's going to do it once, but it can do it more than once. Here's the possibilities. A cubic can do this. It just crosses the x-axis and then carries on. A cubic can come through the axis, double back, just barely catch the axis again, and then carry on. So two x-intercepts. Or the really active ones can go 1, 2, 3. Any of those are possible. So a cubic can have either 1 or 2 or 3 x-intercepts. It can't have 0 x-intercepts, and something that's third degree can't have more than 3, but it can have any number in that range. The end behavior of a graph of degree 3 is determined by the leading coefficient. Okay, we've kind of seen this before, but just to reinforce it, here's an axis, here's another one. If you have positive x cubed, your end behavior is going to be like this. It'll go down to the left, it'll go up to the right. It may have some bumps in the middle, but we don't care about those. We're just talking about end behavior. And if you have minus x cubed, it goes the other way. It starts high and drops. So, if the leading coefficient is positive, they're talking about this, then the right tail goes up and the left tail goes down. If the leading coefficient is negative, then the exact opposite. Right tail goes down, left tail goes up. There are way too many ways to memorize this. I'll let you work one out for yourself. If you're really having trouble remembering it, talk to your instructor and they'll probably share one of their memory tricks. And last sections, consider the behavior of the graph from left to right. Complete the following. Okay, so they're going to describe a graph to us, I guess. The graph starts in quadrant 3, so it starts down here, and it ends up in quadrant 1. What does that mean about the leading coefficient? Is it positive or negative? If it's going uphill like this, then it's got to be a positive leading coefficient. Positive. If it starts in quadrant 2 up here and goes into quadrant 4, that means it's dropping, and that happens if the leading coefficient is negative. And finally, the end behavior of a cubic function is similar to the end behavior of a line. And I'll prove it. If you have y equals positive x, for a straight line, that gives you something like this, that goes from bottom left to top right. If you have y equals positive x cubed, you get a curve that goes from bottom left to top right. It does some horsing around in the middle where it changes direction maybe, but it ends up behaving the same way that a straight line did. And similarly for negatives, if you have y equals minus x, that goes downhill to the right, like so. And if you have a cubic with a negative leading coefficient, those start in the top left, maybe bounce around a little bit, but they end up going to the bottom right as well. So cubics and linear functions, which are degree 3 and 1, it turns out have a lot in common. And it's because they have odd powers. It turns out every odd power behaves like this. If I drew in x to the 5 and x to the 7, they would have this same end behavior.